Today, still section 3.2, two topics. Topic 1, for a function where a derivative doesn't exist. In this topic, I want to answer this question. Second topic, more examples. Have a review about what we have learned. Review number 1. These two formulas are called the definition of the derivative at the point A. The definition says that derivative is a limit. In these two formulas, the point A is a constant. If you view A as a variable, then derivative is a function of A. When something depends on a variable, we call that thing a function of that variable. Review number 2. Computing a derivative is called a differentiation. Derivative is a limit. If the limit exists, then we say that the function is differentiable at the point A. Differentiable means the derivative at the point A is computable, or the derivative at the point A, the limit exists. Otherwise, we say that the function f is non-differentiable at the point A. Review number 3. Derivative at the point A is the slope of the tangent line to the graph of the function f at this point. This point, the x-coordinate is A. Y-coordinate is function value at A because this point is on the graph of the function f. Now, topic 1, where a derivative doesn't exist. Where a derivative doesn't exist, because a derivative is the slope of a tangent line. This question is the same with the question where a tangent line doesn't exist. To answer the question where a tangent line doesn't exist, take a review about what is a tangent line. Simply speaking, a tangent line to a curve is a line that touches the curve and has the same direction as the curve at the point of contact. For example, consider this point on this circle. At this point, there are two lines passing through it. The line L1 is a tangent line, but L2 is not a tangent line. Imagine that I walk along the circle. When I pass this point of contact, my walking direction is this direction. Walk from the other side. When I pass the point of contact, my walking direction is this direction. These two directions are the direction of the circle at this point. Line L matches these two directions. So line L is a tangent line at this point. Example 2. Consider this curve. This point is on the curve. At this point, there are two lines through it. Again, the line L1 is a tangent line. L2 is not a tangent line. Imagine that I walk along the curve. When I pass the point of contact, my walking direction is this direction. walk from the other side, when I pass the point of contact, my walking direction is this direction. These two directions are the direction of the curve at this point. The line L1 matches these two directions. Therefore, L1 is a tangent line at this point. Now, let me show you examples about where a derivative doesn't exist. Here we have 6 figures. The functions in these figures, they don't have derivative at the point A. Now, consider figure number A. In this figure, the graph of the function has a corner at the point A. When a graph has a corner, there no tangent line exists. Because derivative at the point A is the slope of the tangent line at the point A. At the corner, no tangent line, so no derivative there. In other words, derivative there doesn't exist. DNE means doesn't exist. Now, why at the corner, no tangent line? Imagine that I walk along the curve. When I pass the corner, my walking direction is this direction. If I walk from the other side, when I pass the corner, my walking direction is this direction. No line at the corner can match these two different directions. Therefore, at the corner, no tangent line. And therefore, at the corner, derivative doesn't exist. Now, figure number B. The graph of the function in this figure has a cusp at the point A, a cusp. In each side of the cusp, the graph is tangent to this vertical line. At the cusp, the graph has a tangent line. This vertical line is a tangent line. Imagine that I walk along the graph. When I pass the cusp, my walking direction is this direction. Walk from the other side. When I passed the cusp, my walking direction is the same direction. Therefore, this vertical line matches this direction. So the vertical line is the tangent line to the graph of the function at the point A. Because derivative at A is the slope of the tangent line at the point A. So derivative at A is infinity or negative infinity. Because a vertical line, the slope is either infinity or negative infinity. Because infinity is not a number, the book considers that at a cusp, derivative doesn't exist. Figure number C. The graph of the function in this figure has a tangent line at the point A. The tangent line is this vertical line. So derivative of the function at the point A is the slope of this vertical line. It is infinity or negative infinity. Because an infinity is not a number, we also consider that the derivative at the point A in this case doesn't exist. In figures number D, E, and F, the functions are not continuous at a point A. It is a convention. At a point where a curve is not continuous, we assume no tangent line there. Therefore, in each of these three cases, at point A, the graph has no tangent line because derivative at A is the slope of the tangent line at point A. At point A, no tangent line, therefore no derivative. The derivative at A doesn't exist. Example 1. Consider this function. A. Graph the function. What is the domain of the function? B. Is the function differentiable at point 0? Explain. C. Compute the derivative at point 0 by the definition. D. For positive x, what is derivative at x? For negative x, what is the derivative at x? E. Graph this function. What is the domain of this function? Solution to part A. This diagram is the graph of this function. For x less than 0, the graph is the graph of negative x. It is this line passing through the origin with slope -1. When x is greater than or equal to 0, the graph is the graph of x. It is this line passing through the origin with slope +1. The domain of this function is from -infinity to +infinity, namely the set of all the numbers. For example, when x is +3, the function value is 3. When x is 0, the function value is 0. When x is -7, the function value is negative of -7, +7. So the function is computable at any number. Therefore, the domain of the function is all the numbers. Part B. The graph of the function has a corner at x is 0. At a corner, the graph has no tangent line. Therefore, at x is 0, the function has no derivative. In other words, the function f is not differentiable at x is 0. The reason is the graph of the function has a corner at x is 0. Part C. Compute the derivative at 0 by the definition. These two formulas are the definition of the derivative. By this formula, the derivative at 0 is this limit. This limit is a both-sided limit. X can approach 0 from the left, can approach 0 from the right. Because the function f is defined differently on the both sides of 0. go back to the definition of the function. On the left side of 0, the function is negative x. On the right side of 0, the function is x. They are different. Now, because the function is defined differently on the both sides of 0, instead of computing this both sided limit, I compute the left-hand side and the right-hand side limits below. The right-hand side limit at 0. X approaches 0 from the right. That is, x is greater than 0. X is greater than 0, the function is x. So I have this equation. Now, about this fraction, the top is x, the bottom is x. So this fraction is 1, a constant. So the limit is 1. So the right-hand side limit at 0 is 1. Now, the left-hand side limit at 0. X approaches 0 from the left side. X is less than 0. When x is less than 0, the function is negative x. So I have this equation. Now, this fraction is negative x over x. It is negative 1, a constant. So the limit when x approaches 0 from the left side, the constant function negative 1, the limit is negative 1. So the right-hand side limit, so the left-hand side limit at 0 is negative 1. Therefore, the both-sided limit doesn't exist. Because when I let x approaches 0 from the left, when I let x approaches 0 from the right, I got two different limits. So the both-sided limit doesn't exist. Therefore, the derivative at 0 doesn't exist. This result is consistent with the result in part B. In part B, function is not differentiable at 0. So part C confirms this conclusion in part B. Part D. For positive x, what is the derivative at x? For negative x, what is the derivative at x? We can answer this question from the graph of the function. Derivative at x is the slope of the tangent line at the point x. When x is greater than 0, suppose this point is x greater than 0. The corresponding point on the graph is this point. At this point, draw a tangent line. Clearly, the tangent line at this point coincides with this line. This line, the slope is positive 1. So when x is greater than 0, derivative is positive 1. For a negative x, say negative x, suppose this point is x. The corresponding point on the graph is this point. Now, at this point, draw a tangent line to the graph. Clearly, the tangent line coincides with this line. The slope of this line is negative 1. Therefore, for x less than 0, derivative at x is negative 1. We can summarize this result here. Derivative at x is positive 1 if x is greater than 0. Derivative at x is -1 if x is less than 0. Part E, graph this function. What is the domain of this function? From part D, we have when x is positive, the derivative at x is +1. So for x greater than 0, the graph of this function is this horizontal line. The height of the graph is function value. The function value when x is greater than 0, always 1. So the graph is a horizontal line. Horizontal line has the same height everywhere. When x is less than 0, the derivative at x is -1. So for x less than 0, the graph of this function is this horizontal line. The height of this horizontal line is -1. From part C, we learned that derivative at 0 doesn't exist. So this function has no function value at x is 0. So when x is 0, I place open dot, 2 open dots to mean no function value at x is 0. The domain of this function is any number except 0. So the domain is from -infinity to 0. Because -infinity is not a number, I put a parenthesis here to excluding -infinity. At 0, I also place a parenthesis to exclude the point 0. Union together with the numbers from 0 to +infinity. I place a parenthesis at 0 to exclude 0, and also place a parenthesis at infinity to exclude infinity. Infinity is not a number. We should exclude it. Example 2. Let f be this piecewise defined function, where a is some number. Determine a value of a for which the derivative function is continuous at point 1. To answer this question, I roughly, not accurately, plot the graph of function f. On the left side of the point 1, the graph of f is the graph of 2x squared. The graph of this function is this parabola. If x is 1, the function value is 2 times 1 squared. So I put a solid point here. The height of this solid point is 2. Height is function value. It is 2. On the right side of 1, the graph of the function f is the graph of ax minus 2. A is a number. We don't know what the number is. But a number times x minus 2, the graph must be a 9. Suppose the graph of this guy is this 9. I put a open dot here because x is greater than 1. The height of this open dot is plugging 1 in x, plugging 1 in x. The height of the open dot is a minus 2. This is the graph of function f. Now, if the derivative function is continuous at 1, then derivative at 1 exists. Otherwise, the graph of this function will have an open dot at the point 1, and the graph is not continuous at the point 1. Now, derivative at 1 exists. The graph of the function f must be continuous at 1. If the graph not continuous at 1, derivative at 1 cannot exist. The graph of the function is continuous at 1. That means that the open dot and the solid dot, they coincide. Therefore, we have a minus 2 is equal to 2, this equation. From this equation, we get a is 4. This is the answer to this question. Topic 2. More examples. The first example in topic 2. The graph of function f is given in this figure. Part A, find the values of x in the open interval between 0 and 5, at which the function f is not continuous. Part B, find the values of x in the open interval between 0 and 5, at which the function f is not differentiable. Part C, sketch a graph of the derivative function. Solution to part A. From this figure, we can see that between 0 and 5, the graph of the function is not continuous only at x is 1. At this point, we need to remove our pen from the paper to draw the graph. Therefore, the answer to part A is the function f is not continuous at x is 1. Solution to part B. At point 1, the graph is not continuous. So at point 1, the graph has no tangent line. Because derivative is slope of the tangent line. No tangent line there, so no derivative there. Therefore, at point 1, the derivative of the function f doesn't exist. At point 2, the graph has a corner. At a corner, no tangent line. So derivative of the function f at 2 doesn't exist. At point 3, the graph has a cusp. At the cusp, the graph has a tangent line. This vertical line is the tangent line. Therefore, derivative at 3 is the slope of this vertical line. So derivative at 3 is infinity. But infinity is not a number. We still say that the derivative at 3 doesn't exist. At point 4, the graph is tangent to this vertical line. This vertical line is the tangent line to the graph at point 4. Therefore, derivative of the function at point 4 is the slope of this vertical line. It is infinity. So derivative at 4 doesn't exist. Now, the solution to part B is the function f is not differentiable at x is 1, x is 2, x is 3, and x is 4 at these 4 points. Differentiable means the derivative is computable, exists. Not differentiable means the derivative is not computable, doesn't exist. At these 4 points, derivative doesn't exist. Part C. Sketch a graph of the derivative function. We can sketch the graph of this function by collecting some data about the function or by inspection. As an illustration, let me sketch the graph of this function on the interval between 0 and 2 by collecting some data, and sketch the graph of this function on the interval between 2 and 5 by inspection. I make this table to collect data. Between 0 and 2, I pick these points for x. For the derivative at point 1 is about here, close to 0. At x is point 1, I draw a tangent line to the graph of the function f. Now, take a guess on the slope of the tangent line. My guess is about positive 0.2. Therefore, the value of the derivative at point 1 is about 0.2. For the derivative at point 5 is about here. At x is 0.5, draw a tangent line to the graph of the function f. The slope of this tangent line is about 1. So the value of the derivative at point 5 is about 1. Now, derivative at point 9. Point 9 is about here, close to 1. At this point, draw a tangent line to the graph of the function. And then take a guess on the slope of the tangent line. This tangent line is steep. My guess about the slope is about 2. So value of derivative at point 9 is 2. At x is 1, low derivative. So derivative is not computable at 1, so none. At x is 1.1 is here, close to 1, but on the right side of 1. At this point, draw a tangent line. Then the slope of this tangent line is negative, but is a small negative. My guess is negative 0.2. At x is 1.5 is about here. Then draw a tangent line. My guess about the slope of this tangent line is -1. So put -1 here. At x is 1.9, close to 2. At 1.9, draw a tangent line. This tangent line is quite steep. but the slope is negative. My guess about the slope is, say, -5. So derivative at 1.9 is about -5. Now 2. At 2, the curve has a corner, low tangent line there, low derivative there. So derivative at 2 is undefined, low value. Now plot these data points on the xy plane. XY plane. Plot these data points on XY plane. Then connect the points with a curve. Connect with a curve. Then this is a sketch of the graph of the derivative function on the interval 0 to 2. To sketch the graph of the derivative function between 2 and 5, I use inspection. I sketch the graph piece by piece. The first piece is from 2 to 3. Between 2 and 3, all the tangent lines have positive slopes. Therefore, between 2 and 3, derivative is positive everywhere. When x is close to 2, the tangent line there is quite flat. So when x is close to 2, derivative is small. But when x is moved away from 2, the slope of the tangent line is increasing. At the point 3, this vertical line is the tangent line to the graph of the function f. So at point 3, slope is infinity. When x is close to the point 3, tangent line there is very steep. So derivative there is very large. Now, based on this observation, I plot the graph of the function, derivative function between 2 and 3 as this curve. This curve, when x is close to 2, is small, but increasing to infinity. When x is close to 3, the derivative, the value of the function is very large. Now, sketch the graph of this function between 3 and 4. Between 3 and 4, all the tangent lines have negative slopes. So between 3 and 4, derivative is negative everywhere. When x is close to the point 3, tangent line is very, very steep. So when x is close to the point 3, derivative is very large, but negative. When x is moved away from the point 3, tangent line becomes more and more flat. So derivative is dropping from large negative to small negative. But beyond some point, tangent line becomes steeper and steeper again. So beyond some point, derivative is increasing from small negative to large negative again. At point 4, this vertical line is a tangent line to the graph of the function. So at point 4, slope is infinity. When x is close to the point 4, tangent line very, very steep. So derivative is very large, but negative. Now, based on this observation, I plot the graph of the derivative between 2 and 3, between 3 and 4 here. Close to 3, derivative is large and negative. When x approaches 3 from the right side, actually this curve down to negative infinity. Now, when x is away from 3, derivative is, the value is smaller and smaller, but still negative. Beyond some point, derivative becomes larger and larger, but still negative. When x is close to 4, derivative is very large, but negative. Actually, when x approaches 4 from the left side, this curve down to negative infinity. Now, I sketch the last piece of the graph of the derivative function. The piece between 4 and 5. Between 4 and 5, all the tangent lines have negative slopes. So between 4 and 5, derivative everywhere is negative. At point 4, this vertical line is the tangent line to the graph of the function f. So at point 4, slope is infinity. When x is close to the point 4, tangent line is very, very steep. So slope is very, very large, but negative. When we move x away from the point 4, tangent line becomes more and more flat. So slope of the tangent line is dropping from large negative to small negative. So when we move x away from the point 4, derivative is dropping from large negative to small negative. Based on this observation, I plot the graph of the derivative as this curve. Because between 4 and 5, derivative is negative everywhere. This curve lies below x-axis. When x is close to 4, derivative is large but negative. Actually, as x approaches 4 from the right side, this curve down to negative infinity. This curve is increasing because as we move x away from the point 4, derivative is becoming smaller and smaller in absolute value. Example 2. Determine if this function is differentiable at point 0. By definition is here. Derivative at point 0 is this both side limit. If this limit exists, then the function f is differentiable at point 0. If this limit doesn't exist, then function f is not differentiable at point 0. The function value at 0 can be obtained by plugging 0 in the x here. Function value at 0 is negative 5. Since the function f is defined differently on the both sides of the point 0, instead of computing this both side limit, I compute left-hand side limit and right-hand side limit. For the right-hand side limit, x approaches 0 from the right. H is greater than 0. When h is greater than 0, f of h is 3h minus 5. So I have this equation. Now cancel -5, then I have this equation. Cancel h from the top and from the bottom. I have this equation. The function now is free constant. As x approaches 0 from the right side, the limit is the number 3. So the right-hand side limit is number 3. Now, left-hand side limit. For h approaches 0 from the left, h is less than 0. When h is less than 0, f of h is h squared minus 4h minus 5. So I have this equation. Now simplify the numerator. Okay, negative 5, positive 5. Remove the parentheses, then I have this equation. Cancel the number 5, I have this equation. Take out 1h from the top and cancel h, then I have this equation. Now h approaches 0. Plug in 0 in h, then this limit is this number. The number is 4. So left-hand side limit is 4. Because right-hand side limit is number 3. Left-hand side limit is 4. So left-hand side limit and right-hand side limit different. Therefore, the both sided limit, this limit doesn't exist. Therefore, derivative of the function at 0 doesn't exist. So this function is not differentiable at the point 0. I plot the graph of this function here. When x is greater than or equal to 0, the graph is the graph of 3x minus 5. 3x minus 5, its graph is this line. When x is less than 0, the graph of this function is the graph of this polynomial. This polynomial, the graph is a parabola, this parabola. So from this diagram, we can see that at x is 0, the graph has a corner. So at 0, the function f is not differentiable.